So this is from the Greek period. Archimedes, most of you are familiar with, but you may not exactly know what he did in mathematics. You might have heard of Archimedes' principle in fluid mechanics. But he is considered as one of the greatest mathematicians of all times. Along with so Archimedes, Gauss, and Newton and Gauss were generally considered as the three greatest mathematicians in the Western world, at least up to the classical times. So for our purposes, he more or less invented what you now call as integral calculus. He basically calculated surface areas and volumes of several smooth surfaces, right? By what is now called Archimedes' method of exhaustion, which in some primitive sense is integral calculus. Eratosthenes is better known in number theory. He was supposed to have measured the circumference of the Earth around 200 BC using whatever mathematics he had. Ptolemy, many of you would have seen what stereographic projection is, right? Stereographic projection of the sphere onto the plane. So Ptolemy already had given the stereographic projection some 2000 years back. Of course, most of you must be familiar with Euclid, Euclidean geometry, the 5 books of Euclid, and so on. So in our context, he already had recognized that the geodesics on the sphere are great circles. So geodesics are, roughly speaking, paths of shortest distance. In a plane, shortest path from between 2 points is a straight line, right? So geodesics are in some sense of that kind, no, not quite exactly, but so on the surface of the sphere, if you want to go from one point to the other by a shortest distance, the path you have to take is along a great circular arc. A great circle on a sphere is a circle formed by section of the sphere by a plane through the center of the sphere, right? The equator, for example, is a great circle, or the polar circle is another great circle, and so on. So if you take any 2 points on the surface of a sphere, there is a unique great circle through the 2 points, and the shortest path between the 2 points on the surface of the sphere is along this great circular arc. Of course, there will be a small arc and there will be the major arc. So the smaller one gives you the shortest path. So Euclid already had recognized that. So all these, of course, come before the days of calculus. Calculus was invented in the West in the 16th century, 1500 something. Basically differential calculus. Although differential calculus in some form was already invented several centuries earlier in Kerala, especially in North Kerala, apparently. I'm not an authority on these things, but anyway, so the Kerala School of Mathematics, Nilakanta, Madhava, and so on, had some form of differential calculus. Some 3 centuries or so before the time of Leibniz and Newton in the West. Leibniz in Germany and Newton in England. So once they had calculus, of course, differential calculus is a natural tool to study geometry. So post-calculus period, you have Descartes and Clairaut, both from France. They developed what now we call as coordinate geometry, or analytical geometry. Because there were so many Bernoullis who were mathematicians, several generations of them. So the Bernoullis here are Johann Bernoulli and Jacob Bernoulli, who are brothers. Johann Bernoulli and Jacob Bernoulli. And then we have L'Hopital. You might have heard of him, what you call as the L'Hopital's rule for differentiation. He was supposed to have written the first book on differential calculus. He also studied curves and surfaces and introduced the term curvature. You might have heard of him, if you have studied some PDE, you might have seen what is called Clairaut's equation, partial differential equation. Oh, I'm sorry. So, of course, okay, doesn't matter. So, you have a great Euler. Clairaut was the first who studied space curves. So people had been studying planar. Clairaut studied space curves and surfaces and so on. So Euler, I already mentioned, as curves of shortest path on surfaces, some sense. So now, what are called the geodesic equations were introduced by Euler, a set of differential equations. Monge, Dupin, so on. Monge actually had made a lot of contributions to surface theory, different geometry and partial differential equations. We have what are called Monge-Ampere equations. And then comes the real beginning of differential geometry, curves in a plane. And the rendu peru. So Post Riemann, Darboux, the Christoffel, you had a whole school of Italian geometers. Darboux was a French geometer. Lee, of course, was Norwegian. So Christoffel, we have what are called Christoffel symbols, which give you the fundamental forms on a surface, the coefficients. Bianchi, Beltrami, Levi-Civita. Levi-Civita is one person. Okay? So Levi-Civita and Ricci, these are all Italian geometers. You have what are called Bianchi identities, Laplace-Beltrami equation, Laplace-Beltrami operator, Levi-Civita connection on a Riemannian manifold. Ricci curvature had become rather important in recent years because what is called Ricci flow was used to this analysis, okay, to prove a resultant topology called the Poincaré conjecture. Namely, it was Poincaré himself. And Elie Cartan. I'm mentioning Elie Cartan because there is another well-known Cartan, son of Elie Cartan, known as Henri Cartan. So, up to essentially the beginning of 19th century and the end of 19th century and the beginning of 20th century, these are more or less all the important names in development of geometry. Poincaré was one of most profound, and there is essentially no branch of mathematics to which he did not make very important contributions. One of the last, what we can call is universalist in mathematics. His contributions were covered so wide a spectrum of areas. So you can probably say that modern differential geometry basically started with Elie Cartan. So now let me get back to Gauss and Riemann for a brief time. So the first one is Disquisitiones general circa superfiecies curvas. So this is in Latin. During time of Gauss, so on earlier, in the Western world, Latin was the language of science. Everybody wrote in Latin, any scientific investigation. So So this is what that meant. So Gauss, there are two well-known disquisitiones. One is on geometry, the other is on number theory. The other one is called disquisitiones, the arithmetic. So both played very, very important roles in the development of mathematics. Okay, so, and then I'll come to Riemann. The next one is due to Riemann. But let me say a few things about this. Stories, if you like. Gauss was the director of the astronomical observatory in Hanover, Germany. Hanover is a town in Germany. So at that time, it was I don't know, what was it called? Some district kind of thing, whatever it was called. So he was in the astronomical observatory, but the government asked him to undertake a land survey of the district, let's say. So Gauss was doing that, an extensive survey of the land in that district, which is again essentially a piece of surface on Earth, right? So that was what induced him to study geometry of the surface of Earth and in general geometry of surfaces in general. Okay. So he undertook a study of surfaces in general and came out with the definitive work there, in which he proved the most basic fundamental results about geometry of surfaces. Surfaces in R3, okay, two-dimensional surfaces. So, see, in geometry, one of the most important geometrical concept, is the concept of curvature. So, you know, what is now usually called as the Gaussian curvature now. There are two most fundamental results due to Gauss which appeared in this disquisition. One is called land survey. Okay, that is not the thing. Gauss himself called it as theorem egregium. So this means a wonderful theorem. So it is a wonderful theorem, although Gauss himself called it that way. But see, this is a very astonishing theorem. It basically says, we'll say more about it in the course of the whatever it is, course of the workshop. Basically, it says that curvature of a surface is intrinsic. We'll explain more about this later on. The curvature actually is defined, when you look at the definition of curvature, it is not intrinsic. Right? It's calculated using formulae which are not intrinsic. intrinsic, roughly speaking, mean the following. See, you have space and your surface is somewhere sitting in the space, right? So you have an ambient space. So the definition of the term curvature actually involves the ambient space. And the formula you get also formula developed by Gauss himself also involves the ambient space, or the space in which this surface is sitting. But the theorem says the curvature of the surface actually does not depend on the ambient space. Right? Whether how it sits in the space. Okay, so try to say more about this when we come to that. The other is called the Gauss-Bonnet theorem. Bonnet is a name that I have missed there. Bonnet was a French mathematician. So Gauss-Bonnet theorem is another profound theorem which actually has resulted in development of much of modern differential geometry. Basically, the importance of the theorem basically comes from the fact that it connects apparently different let's say quantities. There is a purely topological invariant coming to the picture. There is a purely geometric concept, and there is an analytic concept. The curvature is purely a geometric concept. So what it says roughly is that if you take a surface, let's take say a compact surface, for example, and take the average of the curvature over the surface, which essentially means that you integrate the curvature function over the surface. So the left-hand side looks basically like this, whatever it means. So in case of curvature, this is some area measure. Don't worry about it right now. And so what you have on the left-hand side is a geometric quantity averaged over the surface through integration, so through an analytic process. What you have on the right-hand side is a purely topological number. Number which is purely a topological invariant. What is called the Euler characteristic. So hopefully at the very end of the course we'll say something about this theorem if we have time at that time. Euler characteristic can be also given can be expressed in combinatorial terms. Okay, just I'll say a word, sentence about it. For example, if you take a sphere, divide that into small triangle-like things. Not usual triangle, but triangles lying on the sphere. Or more precisely, if you want, you can let me draw the two things separately so that Are you familiar with the second picture there? It's formed by 4 triangles. Triangle like this. On each side of the triangle, you have another triangle, all meeting at a point. This is what is called a tetrahedron. Okay? So you can, if you like, inscribe the tetrahedron inside the sphere. So, and then flatten out the curved parts there. So topologically, you can identify the sphere with the surface of the tetrahedron. So this is what is called a triangulation of the sphere. So the fact is that you can triangulate any compact surface. So which essentially means you can, topologically, you can build the surface using triangular faces. And then what you do is, so once you look at the tetrahedron, there are 3 kinds of objects there: vertices, and the edges, and the faces. Right? Of course, see, there is no unique way to triangulate. You can further divide this into smaller triangles, for example. Okay? So these numbers are not the same. They don't remain constant. However, Euler said the number of edges minus the number of faces plus the number of vertices is always a constant. E minus V plus F is a constant. So this number is called the Euler characteristic, and that is what you have on the right-hand side of the Gauss-Bonnet. This is a topological invariant. Although I have described it in terms of this triangulation, vertices, edges, and so on, this is topological invariant. If 2 surfaces are homeomorphic, they have the same Euler characteristic. You can express this in terms of homology, what is called some algebraic topological concepts, in terms of what are called the homology groups of the surface. The number of elements in the different homology groups. So anyway, so it is a purely topological invariant. So that's one of the reasons why Gauss-Bonnet is so important. It connects purely geometric quantity with a purely topological quantity. So in general, this is true in mathematics. Anything which connects 2 apparently disparate objects is going to be important. Okay, so I'm not going to say anything about development of geometry in the 20th century and so on, so modern different geometry. I will probably say something my next part of the talk. The thing I mentioned a little while ago about Ricci curvature and the Poincare conjecture, this is quite recent, only not very long ago. So there, again, this problem is a topological one, but the solution came from analysis and geometry through a study of Ricci curvature, flow of Ricci curvature. Flow just means we will also see something about the flow of flows on surfaces in a course. So certain sets of differential equations. That's it for a historical blah blah. So let me now say something about the setting of the subject. What are the geometric objects that you are going to study? What are the kinds of geometric concepts that you are going to look at? So what is the setting of doing all this? The subject is geometry, but there is an adjective, right? Namely differential. So the 2 things, therefore. We are going to study geometry using differential calculus, basically. Okay? So there is also what is called algebraic geometry, which studies geometry using algebraic tools. polynomial, rational functions, rings, right? For us, therefore, we are going to study geometry using calculus, basically, differential calculus. So our objects are all going to be smooth objects. Smooth means smooth, okay? It involves differentiation, okay? So function is not differentiable at a point, there is something happening there, right? You have a corner kind of thing, so it's no longer smooth at that point. If you have a look at this curve, this is not differentiable at that point where it turns like that. There's a corner. So this is not smooth. That is smooth. Of course, we are going to study geometry in a very special setting, simple thing. But in general, what is the setting for doing differential geometry? That's what I will try to say something before we come to a simple situation where we are going to study everything. So basically, therefore, we have to have differentiation, whatever object that you are going to study. You're going to study some space, let us say. On that space, you are to be able to talk of differentiation, right? Differentiability of functions. So differentiability of functions, we know where? Only in Euclidean spaces, R, Rn. So obviously we have to build new things only from things that we already know, we already have, right? So we have differentiation on Euclidean spaces in our kitty, let's say. We have our tools available. So using that, we have to build whatever you want to build now. Also remember that differentiation is a local process, right? The differentiability of a function at a point depends only on the behavior of the function in a neighborhood of that point, right? If you are interested in this point, how the function behaves here is immaterial, right? It's not going to play any part in checking whether the function is differentiable at that point. So what happens near that point? How the function behaves near that point, that's only going to matter. So we express this by saying that differentiation is a local property, right? So geometry differential geometry using calculus, basically. Differentiation. So, what is an obvious thing to try? What are two things that you have in mind? One is, we know, assume at least, we know what is meant by differentiation in Euclidean spaces, right? And differentiation is a local property. So it's natural to look at spaces, whatever they mean, so we want to look at spaces on which differentiation will make sense, right? and then we can try to do some geometry there. So what are the requirements there? You have a space on which you want to do differentiation. To do differentiation, what do you need? We have to build from what we have already. What we have already is differentiation in Euclidean spaces. So you have to bring in Euclidean spaces somewhere to be able to use that. Locally, you don't have to have Euclidean spaces because you want only work locally. Differentiation is local. So if you have spaces which locally are Euclidean spaces, look like Euclidean spaces, we can try to define differentiation, right? So what are we looking at? Trying to look at okay, so differentiation Euclidean spaces in Rn, let's say, in Euclidean spaces. So we look for spaces which look like whatever that look like means. We will come to that. Okay. So we want to try to build up spaces from pieces of Euclidean spaces. The first step, therefore, what do you consider? You must make this more precise. Take a sphere or whatever surface you like, cylinder or anything. Don't look at the sphere as a whole, but look at the patch, small piece of that. Take a point on the sphere and look at a small part of the sphere around that point. How does that look like? The small piece, sphere, you have the point here. So this I'm taking as like this. So if your piece is small enough, it looks more like flat. Okay? But flat or curved doesn't matter. But it basically is a disk, right? Small disk. Maybe a little curved, doesn't matter, still a disk. If you want, you can flatten it to get a flat disk. Anyway, topologically it's the same, right? You can just squash it. So a sphere, for example, looks like a disk locally at each point, right? Or even more basically the real line or a curve, right? Take a curve, take a point on the curve, take a small piece of that curve. That looks like an interval, basically, right? Maybe turned like this, but still an interval. We look for spaces on which such a thing is possible, right? Spaces on which around each point there is a neighborhood which looks like a piece of Rn, a ball in Rn or whatever, some disk in R2. Okay? So look at a space such that, so for every point P in that space, there is a neighborhood of that point which looks like Rn or a ball in Rn or something. But what is meant by this looks like? You have to make that precise. Okay? So topologically is homeomorphic to, right? We said, so this is an interval, not really, but straighten it, it is an interval. Similarly here, disk, not exactly a disk, but only when you flatten it, you get a disk. Flattening is the homeomorphic. So mathematically, what you are looking for is how to make this term looks like precise? Use some topology there. So for each point, there is a neighborhood which is homeomorphic to the ball in Rn, to a ball in Rn, or even to a whole of Rn, doesn't matter. Open balls, any open ball in Rn is homeomorphic to Rn, you know. So whether you say it's a ball or the whole of Rn, doesn't matter topologically. Okay, fine. You look at a space like this. Then what do? What was our object? To try to define differentiation. So in other words, if you take a piece like this and look at a function from that piece to R, let us say, for example. You have a small piece of the sphere here, and you are looking at a function from that small piece to R. So when should we say that this function is differentiable? This is a disk, right? It's homeomorphic a disk. That's what we have assumed. So we know what is meant by saying that a map from a disk to R is differentiable, right? A disk in R2. So from R2 to R, we know what is meant by differentiability. So you have to use that. So you already have a homeomorphism here, okay? So what was our assumption? Every point has a neighborhood which is homeomorphic to a disk, let us say, or a ball in R. So call that as H if you want, or maybe following usual convention. For these charts, you use phi, psi, and so on. Doesn't matter anyway. So suppose phi is this homeomorphism. So you want to define differentiability of this function using what we know already for the differentiability of this function via this homeomorphism. So if you end up with a function from here to here, you know what differentiability means. So how do you, so starting from here, what do? You go to the disk using the homeomorphism and then go to R. So in other words, this is phi inverse in this direction, let's say. So compose phi inverse, and so if you compose this f and this homeomorphism that you are going to have a function from the disk to R. So typically, you would like to define that this function f is differentiable if that composition is differentiable. That means the identification that you make between the small piece there and a disk, once you identify, then the function is differentiable as a function on the disk. That's what it is. So this is what we do, but there is a problem. We resume after the break. You think of what the problem is there. Okay? See, whenever you try to define something, that is something, many times you say, this is well defined. Okay? So what is meant by this well defined? Why you have to, what is that you have to see here? Just think about it, we'll resume it. Resume after the